All right, so let's look at this question here. So question 2 has questions on dimensional analysis, okay? And the most important concepts under dimensional analysis have been asked in this question, okay? So make sure you pay attention and then you know all of them. So all the questions that are going to be coming under dimensional analysis, okay, they will be related to the things that we are going to discuss in this question here. Okay, so the first thing they're saying, give any 3 limitations of dimensional analysis. Okay, so here I've listed 4, but when it comes in the test, you can pick any 3. Okay, so the first one is that dimensional analysis is only applicable to 3 dimensions, okay? Meaning it's applicable to length, it's applicable to time, and it's applicable to what? To mass. That's all. So any other dimension, as long as it's not length, it's not time, it's not mass, then we can't use dimensional analysis, okay? Can't use dimensional analysis. So that's the first limitation. The second one is that dimensional analysis does not give the value of the constant, okay? But the value of the constant can only be known when experiments are performed. Okay, so I'll explain it more later on, but just know that now. And then 3, they're saying dimensional analysis is not applicable to logarithmic, exponential, and trigonometric what? Functions. Okay, so you can't apply dimensional analysis if your equation contains either a log or an exponential or a trig equation, then it won't be possible for you to apply dimensional analysis. I'm also going to explain that in detail. And then the fourth one is that dimensional analysis cannot drive more than one relationship. Okay, and I'll also give an example there. All right, so let's now go into details. By this first one here, what do we mean? Okay, so I've put it here. So dimensional analysis is only applicable to length, time, and mass. So for example, if I have this equation for finding resistance, which is equals to, resistance is equals to voltage over current. Okay, so we know that the voltage, okay, and the current have units that are not of mass and are not of time and are not of what? Length. Okay, so these dimensions here, the voltage or the current, they are not part of the length or the time or the mass. So for such expressions there, we cannot use dimensional analysis, okay? Or in simple terms, we cannot use dimensional analysis to drive this formula here. Why? Because it does not contain the length, time, and mass. It contains some other things. Okay, so we cannot drive this formula directly using dimensional analysis. So that was limitation number 1. The other limitation is this one here, and I've also written the third one here. So we're saying dimensional analysis does not give the value of the constant, right? Okay, so for example, if you want to derive the equation of the pendulum and the period, okay, what you have here is that you have something like this. Okay, so T is proportionally equal to the root of L over what? G. So this symbol here is called a proportionality symbol. So you always replace this proportionality symbol with equal to K like this. Okay, so whenever you see this symbol here in dimensional analysis, it's the same as equal to K. Okay, so equal to K simply means this K here is a constant. Okay, so this relationship simply means T, this one, and then I replace this guy with equal to and K, and then I write L over what? G. So now using dimensional analysis, you cannot know the value of this constant here. Okay, you cannot know the value of this constant here. You can only know the value of the constant if you carry out some experiment. Okay, so the value of the constant in this formula is 2 pi, but we cannot find it directly using dimensional analysis. Instead, we're going to use experiments to find this. Okay, so that's another limitation. And then the third one that I talked about, I said dimensional analysis is not applicable to logarithmic, exponential, and trigonometric functions. So an exponential example is this equation here. Y is equals to A and then e to the power kx. Okay, so because this kx here is an exponent, okay, then we cannot use dimensional analysis, okay, to derive this formula. Okay, because this one here simply means the kx must be dimensional. It must be dimensional, dimensionless. Okay, the kx there. That's what this means. Okay, but using dimensional analysis, we fail to derive the relationship there. Okay, so that was the third limitation. And even this one here, you can see there's a trigonometric ratio there. So we cannot use dimensional analysis to derive such equations. The fourth one was what? Okay, the fourth one was, let me go back here. I said you cannot drive more than, dimensional analysis cannot drive more than one part of the equation. So for example, okay, if my equation is maybe A is equals to B plus C. What we mean by this fourth point is that, okay, at one particular time, I can only find the relationship between A and B using dimensional analysis, okay? Or I can find the relationship between A and C, okay? I cannot, however, find the relationship between A and B and C simultaneously at one point. No, it doesn't happen like that, okay? So this one here can only be related to this at one particular independent point, or it can be related to the C at one particular independent point. So yeah, so those are the limitations of dimensional analysis. And then someone might ask, what do we use dimensional analysis for? Okay, so we've been doing it uh, when you're converting units, okay, you can use dimensional analysis, okay, when we are converting units. The other use of dimensional analysis is when you are checking the consistent of equations that you have, making sure that the units that you have on the left are the same units that you have on the right. So we use dimensional analysis. Okay, and then the other use of dimensional analysis is when we are deriving equations of certain relationship. Okay, so I've explained that, okay, and then now I move to part B. So here you see that on part B, we'll be using dimensional analysis uh, to convert units, okay, from one unit to the other. So here they're saying a driver moving at 40 meters per second, okay, passes a traffic sign that indicates that his top speed must exceed 60 kilometers per hour. So the question now, has he exceeded the speed limit? Okay, so the speed sign is in kilometers per hour. They've given us his speed in meters per second. So meaning we have to convert this, okay, to kilometers per hour and then see if that value will be greater than or it will be less than the 60 kilometers per hour, which is on the sign post there. So how do we convert this? Okay, we use dimensional analysis. So first of all, we state the conversion factors between meter and kilometer and second and hour. So we know that 1 kilometer is simply equals to 1,000 what? Meters. And then 1 hour is simply equals to 3,600 seconds. Okay, so let's use dimensional analysis now to convert. So this will be 40 meters. This second goes to the denominator. And then I'll say multiplied by dash, multiplied by dash. So I'm going to arrange these conversion factors in such a way that this meter should cancel and this second should cancel. So if this meter has to cancel, since it's on top here, I'm going to write it down. So 1,000 meters, and then I write 1 kilometer. Okay, and then here I'll put this conversion factor such a way that the S should cancel. So the S is down here. Here I'm going to put it on top. Okay, and then 1 hour here. Okay, so we see that the M and the M cancels out, the S and the S cancels out. So I have 40, okay, multiplied by 1 kilometer, multiplied by 3,600, okay, and then divided by 1,000. So what do I get there? Okay, so I'll just do 40 multiplied by 3,600 there. Okay, so 40 multiplied by this guy, I'm going to get 144,000 divided by, okay, don't forget the kilometer, divided by the 1,000 here, which is hour, because this 1,000 is multiplied by the hour. So we see that we can cancel out these zeros here, or you can simply punch it directly on the calculator. So you're going to get 144 kilometers per what? per hour. So this speed here, the 40 meters per second, is the same as 144 kilometers per hour. But the speed limit said 60 kilometers per hour. So this driver is way above the speed limit. Okay, so the question was, has he exceeded the speed limit? So our answer there would just be what? Yes, he has exceeded because we are finding this speed as 144 kilometers per what? Per hour. Okay, so any questions there, guys? Any questions there that you have before we proceed? Okay, so if there are no questions, let's continue. So the next thing now is a very important rule that we use in dimensional analysis. Okay, so basically there's just one very important rule in the dimensional analysis. So that rule says that, okay, you can only add or subtract quantities with the same dimensions. So in other ways, they're saying we can only add or subtract quantities with the same units. Okay, so for example, if I have 10 meters minus 5 meters, I'm allowed to subtract here. The answer will just be 5 meters. Okay, but if I have maybe 10 meters, okay, minus 5 centimeters, okay, can I get the answer here? No, unless I change one of these to the other units. It's either I change the centimeter to the meter or I change the meter to the centimeter, then I can subtract. Okay, so we can only add or subtract um, units, I mean quantities that have the same dimensions. Okay, so if they gave you an expression, they saying maybe they say p minus k. Okay, and then they say p, okay, has the dimension t. What is the dimension of k? Okay, so because there's this minus sign there, okay, they are subtracting these two. It means even the k has the same dimension as the what? As the p, because we can only subtract or add things that have the same dimension. Okay, so in other words, we're saying the dimension of what we have on the right side should be exactly the same as the dimension that we have on the left side. Okay, so that's what we're going to see in this question. So this question, they're saying if y is equals to p plus qt plus rt to the power 3, okay, where where y is measured in meters, okay, t is measured in seconds, what are the units of p, q, and r? So this is a very simple question, okay, but if you don't know this rule, then your head will start spinning, and then you won't get it, you won't get it correct. Okay, so here they've given us the units of y and t. So since we have the units of y and t, we can easily get their what? Their dimensions. Okay, so y, been told it's measured in, okay, or y has the units meters, and then t has the units second. So the dimension for meters, which measures length, is just what? L, like this, okay? And then the dimension of s, which measures time, is just the capital letter T, like this. So those are the dimensions there that we are dealing with. Okay, so those are the dimensions that we are dealing with there. So you notice that on my left hand side here, I only have y. Okay, I only have y there. So y has the units m. Okay, so simply meaning everything here, okay, because I'm adding them like that, okay, everything here should have the same units as this m here, okay, because if I have meters here, then I can't have centimeters there, or I can't have kilometers there. Then this thing won't make sense because they're saying this thing is equal to this. So the units that are here should be the same as the units when I combine all these here. Okay, so I have y is equals to p plus qt plus rt to the power 3. So since the units of this y is just meters, it simply means this guy here, the p, is also meters because it's just standing alone. Okay, it's just standing alone. And then when I combine q and T, okay, the units there should also be what? Should also be meters. Okay, plus when I combine R and T, the units there combined should also be meters. So that when I add meters plus meters plus meters, I get what? Meters. That's when it makes sense. Okay, so the units for P, we've already found it. It's just meters. Okay, what about the units for Q? So Q, okay, uh, is being combined with the T. So QT, okay, the units for these guys should lead to a meter. So now I'll write here, okay, I'll write here as um, Q, and then I put the units of time because the units of time I have, they were given as seconds. So time should be equals to the units that I get there, which is just what? Meters. Okay, so meaning that I can divide both sides by S, divide both sides by S. So the units of Q are simply going to be what? Meters per second, or you can write them as meters S to the power minus 1. So these here are going to be the units for Q. So that when I multiply with the time, okay, the S is going to cancel out and I'll just remain with the what? With the M. So that this addition here makes sense. Okay, so the units for Q are just simply what? Meters S to the power minus 1, or meters per second. You can also say it like that. What about for R? For R, it's the same scenario. When I combine the units for R and T to the power 3, I should get a meter. Okay, so I'm just going to say R multiplied by, and then the units for T, I know it's S, and then it's cubed there. So I put the power 3. This here should be equals to a meter. Okay, so meaning R will just be equals to M, and then I divide by S to the power 3 on both sides like this, or simply M S to the power minus 3. So the units for R are simply M S to the power minus 3. So that when I multiply, okay, the units of R with these units of time S to the power 3, the S to the power 3 is going to cancel out. I just remain with the meter. So that this addition here makes sense. Okay, so that's how we can find the units of P, Q, and R there. All right, so any questions there? Any questions before we move? Okay, so that was part C. Let's look at part D. Okay, so now part D is deriving a relationship between given quantities. Okay, so you can see here part D, they're saying a particle travels at a constant speed v along a circular path of radius r. Knowing that the particle's acceleration a, okay, so there's v r, and then the particle's acceleration a depends on its speed and the radius r, okay, of the orbit. Use dimensional analysis, okay, to determine an expression that links acceleration, speed, and the radius. Okay, so what are we going to do there? Okay, so what are we going to do there? So it's very simple. Okay, so it's going to be very simple. So the first step when you are deriving an equation, okay, the first step when you're deriving an equation is to write A. Okay, to write A is proportionally, okay, related to the V and the R. So what do we mean by that? We're just going to write A, which is the acceleration, is proportionally, okay, related to V and R. So now on this V, you're going to put a power. So any letter of the choice. So here I'll choose X. And then even on the R, you're going to put a power like that. Okay, so that's the first step. Okay, you write that A is proportionally related to the what? To the V and R, and then you raise the V to a power of your choice, and you also raise the R to the power of your what? Your choice. Okay, and then after that, we're going to replace uh, the proportionality symbol. Okay, so someone has raised their hand. Bernard Walia. You have a question? I've seen your hand. All right, maybe it was a mistake. Okay, so this was the first step here, just writing that acceleration is
Yes, sir.
proportional to the,
So
oh, yes.
I want to ask, yeah, why are you putting powers to V and R?
Okay, yeah. So we are trying to derive an expression using dimensional analysis between the acceleration, the speed, and the error. Okay, so I was explaining now that the first step, okay, this is always what you do, is to write A, because here they said A depends on V and R. So that means that A is proportionally related to the V and the R. So this symbol here means proportionally related. So A is proportionally related to the V and the R. And then now, each of these quantities on your right-hand side here, you are going to raise them to a certain power. Okay. Why are we doing that? Because we are trying to establish a relationship. Okay. We're trying to establish a relationship. So um, in the actual equation, once we derive it, okay, this V here might be raised to a certain power, and this R here might be raised to a certain power as well. Okay, no wonder we're putting X and Y there because we don't know if V is raised to a certain power and if R is raised to a certain power. So we just put arbitrary powers there so that in case they're there, then they'll come out as we are trying to derive. But in case they are not there, then you just find the X to be 1 and the Y to be 1. So that's why we're putting X and Y there.
Okay, thank you, sir.
All right. So this is the first step. And then the second step is to replace this proportionality symbol. You've seen it. Okay. You always replace it with the equal to K. Okay. Always replace it with equal to K. So I'm going to write this as A is equal to K. And then I write V to the power X and then R to the power what? Y. So that's the second step. The third step is to replace each quantity with the SI units. Okay, so by now you should know the SI units for acceleration, for speed, and also for radius. So acceleration, okay, it's SI units. We just know it's meters per second, right? Squared. This is for acceleration. And then for speed, we know it's meters per second. And then for R, which is just like a distance because it's radius, it's just meters. Okay, so these are the SI units for these things. So I'm going to replace them here. So now this M per second squared, okay, is the same as M divided by S to the power 2, which is the same as M S to the power minus 2. Even this guy here is the same because the S here means it's in the denominator. So it's the same as M over S, which is the same as M S to the power minus 1. So why are we doing this? We are using the properties of indices. Okay, we're using the properties of indices or exponentials where we said if I have A to the power minus N, this is the same as 1 divided by A to the positive power. Okay, so there we had S to the power 2 in the denominator, which means it's the same as S to the power minus 2 in the numerator. Okay, so I'm going to replace this with this guy here. So it will be M and then S to the power minus 2 is equals to, I write my K, and then this V here, okay, I replace with SI units. So that will just be M S to the power minus 1. So this is just for V. Okay, don't forget that the V there is raised to power X. Okay, and then the other one is for the R. So for the R, the SI units are just meters. Okay, and then forget that these are raised to power what? Y, like that. Okay, so once you do this, um, it's now to replace the SI units. Okay, you replace them with the dimensions. Okay, so we said the dimension for length, okay, or for distance is simply capital letter L, like this in brackets, okay? And then the dimensions for time, it's capital letter T in brackets like this. If you want, you cannot put the brackets, there's no problem. And then what other dimension do we have here? We just have length and time, okay? So that's what we're going to put. So this one here is going to be, for the M, the dimension is the L. So I'll just write L there, okay? And then for the S, the dimension is the time. So it's raised to power 2, and then is equals to K. And then inside the brackets, this guy here is L, okay? And then this guy here is T to the power minus 1, power X. And then here, the M would just be L. Okay, the M will just be L to the power Y, like this. So that is what we have. And then let's distribute the X here to everything that we can see here. So I have L T to the power minus 2 is equals to K. And then uh, this guy here, the L, okay, we distribute this power to whatever we have inside there. So the L, okay, is now raised to power X because the X goes to the L, okay? And then from there, uh, the X goes to the T to the power minus 1. So I just get T to the power minus X like this, okay? And then the other guy there, the L, gets L to the power what? Y. So that is what I have there, okay? And then from there, what am I going to do? I'm going to add like terms. So on my left, I have L T to the power minus 2 is equals to K. And then here, I can see L to the power X, okay, being multiplied with L to the power Y there. So I'm simply adding X plus Y because the base is the same. And then I have T to the power minus X. Okay, so you see now what we have there. Okay, so we're now going to equate, okay, the power of L on the left to the power of L on the right, and the power of T on the left to the power of T on the right. Okay, so this K here is just a constant, so it's dimensionless. Okay, so if you want, you cannot write it in the equation. Okay, so you can see the power of L here is just 1 because there's no power. So I'll say 1 is equals to X plus Y here. And then here, the power of T is minus 2 is equals to the power of T here is minus X. So what does this mean? Okay, so here I'll just divide by a negative both sides. So X will just be equals to what? To 2. Okay, so if X is equals to 2, well, then what will be my Y? So that would be 1 is equals to 2 plus Y. So Y is equals to 1 minus 2, which will just be minus 1. So Y is equals to minus 1, like this. Okay, so we found the values of X and Y, and then we can take them back in the equation. So let's do that. So the equation that we had was this guy here. So I'll erase this part. Okay, so it will be A is equals to K. This will be V to the power X, which is 2. And then R is simply, Y is simply minus 1. So if the power is a minus 1, it goes to the denominator. So this will be A is equals to K V squared over R. Okay, so we have derived uh, the expression that links the acceleration, the velocity, and the R there. Okay, so here, because we haven't been given the value of K, okay, the value of K, we can only get it from the experiment. We're going to say K is dimensionless, okay? K is dimensionless, but you can state, okay, so for this question here, it's a very common question in the exam and in the test, okay? You can say from experiments, okay, from experiments, K is equals to 1. But if you don't have any idea what the value of K is, okay, you just leave it here and then you say K is a constant, so it's dimensionless, Okay, so from experiments that have been conducted before by scientists, K is found to be 1 in this equation. So the final expression is just A is equals to V squared over R. So now, when you reach at a point where you'll be finding or when you reach rotational motion, okay, you'll be using this formula here to find the rotational acceleration. Okay, you'll be using this formula to find the rotational acceleration when you reach rotational motion. Okay, but for now, we're just driving a formula using what? Dimensional analysis. All right, so any questions there, guys? Any questions there? Okay, if there are no questions, this is the end of part T. This was question what? Was it question number 2 or something? Okay, so that was question number 2. Let's now go to question number 3. Okay, so I'll put it in a separate recording